In this video, we talk about borazine, also known as inorganic benzene. It has similar physical properties and its structure to that of benzene ring, which we will see. Therefore, it is also known as inorganic benzene. Talking about the preparation, how can borazine be prepared? There are three particular methods of preparation. Out of these, one of the most important method of preparation of borazine is by the reaction of diborane. When you react diborane with liquid ammonia in 1:2 molar ratio, it means if 3 moles of diborane are reacting, it's twice, that is 6 moles of ammonia will react at 250 to 300 degrees Celsius to form borazine. B3N3H6 and 12 molecules of hydrogen are released. This is borazine. Borazine, this is the first method. Second method is by the reaction of boron trichloride with that of ammonium chloride at 150 to 160 degrees Celsius. This forms a trichloride product of borazine. This product is further reduced by sodium borohydride, that is a reducing agent, results in the formation of borazine. And these are the byproducts formed, right? Third method, again resembling the second, preparation of borazine by sodium borohydride with ammonium chloride. This is ammonium chloride and this is sodium borohydride. NaCl is formed as a byproduct again, results in the formation of B3 N3H6, that is borazine, plus NaCl along with 9 moles of hydrogen gas. These are the three methods of preparation of borazine. Talking about the structure of borazine now. Its structure is very much similar to that of benzene. Structure of benzene looks like this. Right? With alternate double bonds and 6 hydrogen atoms attached to every carbon. And these carbons are sp2 hybridized, right? Structure of borazine contains boron and nitrogen in alternate forms with the presence of alternate double bonds on them. And hydrogen atom attached to every single boron and nitrogen. 6 hydrogen atoms, 3 nitrogen and 3 borons forms B3N3H6 that is Borazine. Here again, the N atom, the nitrogen atom, has a fully filled orbital, whereas boron, again being electron deficient, has empty p orbitals. Therefore, the transfer of electrons will take place, as we discussed in the previous video in back bonding. Here, the specific term called dative is used. I'll explain you how and why. So, taking into consideration the orbital diagram, we have this structure, boron, nitrogen. If we invert it a bit, in the same plane, this is the general structure. We are not making hydrogen atoms for the sake of understanding. Now here, the black marker represents fully filled orbitals of nitrogen, whereas these red ones mark empty orbitals of boron, since boron is electron deficient. Now what happens is, electron pair, the lone pair from the nitrogen, is shared with that of boron. Is shared with that of boron. This is the fully filled orbital. This is the vacant or empty orbital. Lone pair of electrons from nitrogen is shared with that of boron, results in the formation of a coordinate bond. It already had a covalent bond between them. Another coordinate bond is formed. Therefore, we state that the pi bonding in Borazine, that is this bonding, this double bond has one sigma bond and one pi bond. This pi bonding is dative and it arises from the sidewise overlapping of the fully filled nitrogen and empty p orbitals of boron. Right? Therefore, we say pi bonding in Borazine is dative. Dative means it has a coordinate covalent bond. Coordinate covalent bond. That means there was already the presence of a covalent bond between nitrogen and boron. The nitrogen further shares its electrons with that of the empty orbitals of boron, forming a coordinate bond, resulting in dative pi bonding. Thus the structure. Now, talking about the properties of Borazine. First of all, Borazine, its physical properties, it is colorless, having a melting point of minus 57 degrees Celsius and a boiling point of 55 degrees Celsius. Its physical properties are closely similar to that of benzene. Talking about the chemical properties. Borazine readily reacts with water. The reaction is similar in that of any alcohol or with hydrogen halide, that is the hydrogen acids HCl, HBr. This results in the formation of addition products, that is BH hydride, hydroxyl group and an amide group, right? And if this is reacted at 100 degrees Celsius, this is the addition product formed. See, borazine is more reactive than benzene. Thus, it forms addition product. Since borazine is more reactive than benzene, it gives addition products, and when we heat this addition product at 100 degrees Celsius, it loses hydrogen. It loses an hydrogen atom. 3 moles of hydrogen are reduced, and for this reaction to take place, the molar ratio of the reactants has to be 1:3. 1 mole of borazine reacts with 3 moles of water or alcohol or hydrogen halide to give the addition product, which on boiling reduces hydrogen. Similar reaction occurs with alcohol. If we should write B3N3H2 borazine plus 3 moles of alcohols will form BHOR NH2 whole thrice, and on heating it at 100 degrees Celsius, it will reduce these hydrogen atoms. One from here and one from here results in the formation of BORNH whole thrice plus 3 moles of hydrogen are released. Another important property is when we pass silent electric discharge through borazine. When we pass silent electric discharge through borazine, it results in the formation of this product called inorganic naphthalene. That is a product that closely resembles naphthalene, like this. Okay. Also known as inorganic naphthalene. Right? This is another astonishing property of borazine, which on passing through a silent electric discharge results in the formation of inorganic naphthalene, right? Also, when we react, another last property of borazine is on reaction with HCl, it forms B3N3H9Cl3, which you can omit, and we can directly write on reaction with HCl in the presence of sodium borohydride, a inorganic cyclohexane is formed, which is similar to cyclohexane or analogous to cyclohexane, B3N3H12. Now here all the pi bonds are reduced to sigma bonds, like this. similar to that of cyclohexane, except in cyclohexane, boron and nitrogen atoms are replaced by all the carbon atoms.